All right, here we go. Welcome, everyone. Good evening. It's my pleasure to welcome you guys to this session, as well as to welcome Yasiru Ratnayake, who is the head of data science at Search Global. Yasiru has done a session at PyCon last year as well, so some of you might remember it. Um, so before I hand things off, I would like to make an announcement that we are organizing PyCon 2023 in the next year, and right now we are looking for volunteers to help us organize the event as well as speakers. So if you go to pycon.lk, you'll be able to submit your details via the forms available there and look at more data there. So thank you very much, Yasiru, for taking the time to join us and get going with what I am sure will be a very interesting session. Over to you.
Thank you very much, and thank you everyone for joining this one. I thought to do something a little different from what I'm usually used to. I'm not going to use slides. I'm going to try with a Jupyter notebook, and I ideally like for it to be a bit more of a interactive session. So if you're gonna, if you're able to stop and ask questions, I may also try to pose questions to you. And we can kind of keep it a little interactive. The abstract probably gave away the fact that this was a fairly eclectic set of different topics that I've pulled together, all under the name of streaming and learning on streams. So we might be spending less time on each one, but I'd like to, certainly expand if there is audience interest for each of those sections. So without further delay, let me just get started. Share my screen. Okay, I hope everybody can see my Colab notebook here. I'll be sharing this one later on. Stop me if you don't see it, but I'll get started. So in terms of this particular talk, if you've read the abstract, what I'm really interested in here is about data sets that come to you not in the form of a nice CSV file or a nice table in a database, and not so nicely sized, and not with the the kind of velocity of data arriving at you that you can easily handle. What I'm more interested in here is about massive data sets that are through some process they get generated, and they get generated incrementally, or you receive them incrementally, or a combination of the two. So we call these data streams. And usually the problem is that it's more about velocity rather than necessarily volume. So you might not have a huge data point coming through, but you'll have so many data points coming at you so fast that it all amounts to a huge data set in a given window of time. So instead of the kind of techniques that we use to analyze such data sets as batches, we have to start thinking about how can we deal with this kind of stream data. So this kind of data can occur pretty naturally in a lot of different settings. We're going to look at a particular setting today that is financial markets. We're going to look at some stock data. We're not actually going to deal with the kind of data volume that I'm talking about, partly because this is a collab and partly for your understanding. I think it's better to deal with smaller data sets. But other than financial markets, you would find this kind of data in web clickstreams. Right now, computational advertising is a very big industry, and companies like Google and Facebook handle clickstreams where users show interest in one thing versus another, and those feeds are of gargantuan size. There's also a lot of sensor readings floating around in terms of Internet of Things, and that sort of thing. And there's, of course, video and audio feeds, and there's so much more of that data being created continuously today than ever before. So what we're going to do in terms of the agenda is we're going to try looking at what this kind of data looks like, and we'll kind of motivate ourselves with financial markets. We'll try to see if we can actually simulate such data ourselves. And in doing the simulation, we'll look at how can we represent such data in such a way that you're not going to run out of your RAM, or it's sufficient for your computer and perhaps even the core that you're working on to handle it in a incremental kind of way. Once we have a bit of a handle around the data, I'd like to explore something called sketching. So with sketching, this is a way of getting a summary of the data that you're interested in. So sketching, particularly for streaming data, and particularly for statistical properties of that data. This is particularly going to be about the distribution of the data. We're going to touch on that, and we're going to look at a method called t-digest. We may not be able to go into the details of how it works, but I'll try to sketch that for you as well. And lastly, we'll touch on some libraries that allow you to model streaming data. And we'll see how the APIs for these libraries are, somewhat hewing very close to the batch setting that we're all somewhat comfortable with. And I'm not assuming too much of the audience, but you may be more familiar certainly than with the batch setting than the streaming one. So to get started, let me just collapse this over here. To get started, let's look at getting some data in. So I've got some imports here. I've got pandas. I've got something called pandas data reader. And pandas data reader is a nice little tool that allows you to get web data and other sorts of, it's primarily around web data. So you can get pandas data reader.data as web. That's your import. I'm getting some date times to help me out. But what I'm going to try to do is download the price series for some stock tickers. As you can see, these are around Tesla, Apple, Amazon, Netflix. These are all kind of tech stocks. These last two are Coinbase and NVIDIA, if they seem less familiar. But what I'm going to do is I'm going to download those from today, and then looking at I'm actually going to get it from yesterday, and I'm going to look back 120 days. So the way you get it is by calling this data reader, this data reader object. I want to instantiate that. So I'm going to feed it the tickers that I'm interested in. And out of the data sources, I think Stoch is the one that hosts the formerly Google Finance API. So we have that one. I'm going to pass in my start date and the end date. And what I'm interested in particularly is the closing price for these stocks on each of these dates. So I'm going to run this dictionary comprehension. So for each of these tickers in this list over here, I'm going to fetch a kind of key value pair where the value is the price series. So if I do that, I'm going to end up with this data dict. And I'm not going to try this just in case of, internet issues, but we can certainly run this. But I'm going to just tell you what would happen. So with this data dict in place, I can just convert that to a pandas data frame, and we're off to the races. So first, getting a data set, we'd want to look at this, and this is still in the kind of batch setting. Now we've got a data set, and it's got a particular shape. So I'm going to import plotting library Plotly Express as it happens. I'm going to look at a line chart for these prices, and I'm going to look at the closing values on the y-axis, and I'm going to look at the dates on the x-axis. and the different tickers are colored differently. So I can see here where I'm hovering, Microsoft on the 12th of September closed at $266.65. So this is a fairly small data set, and we're still looking at it from a batch kind of setting. But I'd like to spend a bit of time to understand this data set. So typically, in a financial analysis, what you want to do is you want to look at the returns. And there's a reason for this, because there's a fairly rich theory around Brownian motion, and especially geometric Brownian motion, that is a model for asset prices. So while this isn't the kind of analysis you might actually do if you had money on the line, it's certainly not financial advice. A standard step would be to look at the log of the return series. So I'm just shifting the data by one. So this is your current current data, and this is your 1 day past data. I'm going to take the log of that return value. So these are called returns. I'm going to drop NAs because there's going to be an NA at the end. And I'm just going to plot that as a line again. So now you've got this kind of series. And the nice thing about this series is it's in a much more tolerable kind of scale. We know how it moves within this scale, but it's really the same kind of series as I had before. What you want to be looking at, though, is about the empirical distribution of these series. So what I'm going to do now is I'm going to look at these log returns that I just generated, and I'm going to try to plot them as empirical CDFs. So if you've not seen this kind of plot before, this is just like a cumulative distribution function. But this is the cumulative distribution function on the real data. So if you've worked with distributions, for example, the normal distribution, you'll see a cumulative distribution function rather like this, and this tells you, at a given point how much of the probability mass is on the left of it by looking at the area under the curve to the left of that point. And you can see here, this is not very unlike what you would get from the theoretical distribution of normal, but this is the empirical. So this is really based on the data. So I'm going to do this for each of these ticker symbols that I have here. And at the top, I'm just going to plot the marginal. So this marginal is actually something that looks kind of normal. You can see a bit more spread versus less, and it's not too much data points, but and maybe there's some still some skewing that the log hasn't really picked up, perhaps. You could argue for these things, but the standard model is to consider these things as normally distributed. What I do then, I'm interested in these returns. I want to model them. One thing I want to do perhaps is look at whether these assets are correlated. Certainly, if I look at what the assets are, Tesla, Apple, Amazon, they're all kind of big tech assets. So you would expect some sort of correlation just from the industry sector. And indeed, just plotting these as scatter plots, you can see that there's there's certainly some sort of pattern going on here. How do I quantify that pattern? Well, I can just call the core method on the log returns data frame, and that will give me the correlations. I'm going to use Plotly again to show, to show the figure of the correlogram. So you can see there's high correlations. It's kind of going from 0 to 1. So you can see there's fairly high correlation everywhere. Even the lowest tends to be something like 0.57. So I have reason to believe that this data is correlated. So if I wanted to simulate it, I'd have to take that into account. I can't simply simulate based on the last value and simply do a random walk. So in order to do that, I need a few things in hand. So what I'm going to do is I'm going to look at the mean of these series. I'm going to look at their standard deviations. So I'm putting these into, so I had something like 8 tickers. So this thing has, 8 means has 8 items. Similarly, standard deviations has 8 items. I also have 8 items as my initial prices. So I'm just going to look at the end of this, just the way this data frame comes. You might want to be um, careful of the ordering. You have an index and that is the date. So I'm looking at it from the other way. And then we get to kind of trying to simulate these. So the reason we want to simulate these is that we want to look at future price paths, and in particular, these future price paths could be easily our stream of data, right? So what we can do is look at what is a suitable mathematical model to do that. And in this case, I'm using the Black-Scholes-Merton model. This is fairly famous under the moniker of the Black-Scholes model. So this is a what's called a stochastic differential equation. I'm not actually showing you that form of this at the moment. What I'm instead showing you is what's called a difference equation. And the reason for that is that you're, showing increments that are not continuous. So these are discrete increments. I'm going to show you with ST, that's the price at time t. And I'm going to show that to you in terms of price at a discrete time prior to that. This is this delta t. And the way you get that is per the model, you take the exponential of what's in here. And you have certain numbers that are kind of more of an interest if you're into finance. So this R is your risk-free rate. You've got your volatility. So this is simply the, actually this is the volatility squared because this is the variance divided by 2. You've got your delta t coming in again. And to this, you add another term. This is the volatility into the root of the increment. And then there's a z here. So this z is actually a standard normal distribution. And this is the kind of model that you would use. But we had a little bit of a complication in what we looked at because we found out that we had this kind of correlation in our data. So what are you going to do about that correlation? Well, you have to figure out a way to incorporate that when you're actually using this Euler scheme to generate Monte Carlo price paths. So let's actually try that out. And what I'm going to do is I'm just going to do some imports. Mainly, I'm just giving type hints over here. So I'll skip over that. But what I want to do is look at some interval, some look-ahead interval t, and I'm going to generate this dt that I need. I have these prices that I'm going to store in this kind of array of, it's t steps ahead, but this t plus 1 because I want to store the initial price that I'm going to base all of this, simulation on. So it's t plus 1, and then I have, n assets, and that's going to be 8. So I needed those initial prices. So that's something I'm taking in. I'm also going to need those log return correlations that I plotted. And I'm going to need things like the standard deviations. So what am I going to do? I'm going to use NumPy's random submodule, and I'm going to generate some standard normals. So this is centered around 0. It's got a standard deviation of 1. And I'm going to get 8 of these things because I'm iterating over the time interval. So you'll notice that this particular method has an interesting feature, and that is that I'm using yield instead of return. And this yield, you can see, is actually inside the for loop. So there's a reason for that, and the behavior will be apparent when I show you what you can get out of this. So what I'm going to do is I'm going to take these random normals, and I'm going to actually handle the correlation issue. So a standard way to handle the correlation issue is to take a dot product with what's called the Cholesky decomposition of the correlations. And that's why I really needed the correlations. There's a bit of theory here, but I won't actually, go into why you need it. Some of it is actually, coming up over here, but you might want to, look that up separately if finance is something of interest, or linear algebra for that matter. But once I do have these correlated normals, what I can do is I can sample prices for each of the tickers. So I'm going to go over my range of, however many stock tickers I had, and I'm going to take the standard deviation for that one, and I'm going to set the next price. It's the prior price times, what we saw in the equation. This is exactly that equation. And then I'm going to yield these prices, and this yield is inside this first for loop. And the reason for this is actually a generator. This is a special type of function. We call it a coroutine. So the reason that we call it a coroutine is that if you're familiar with iteration in Python, you have iterables. These are things like lists, and you call them iterables because there's some sequence to them, and particularly you can create iterators out of them. So iterators are things that give you one at a time their values, and they exhaust themselves. A generator is simply it could be a function, it could be some routine. It gives you these iterators back. So generate prices here is a generator. And the way you would define a generator, one of the methods at least, is through this yield keyword instead of return. And the way this works, I'll just illustrate it for you, is I'm going to actually instantiate something called stream. And to generate prices, I say I want 120 steps ahead. I'm going to use a risk-free rate of 1%. I have this many stocks. I have these standard deviations, initial prices, and I have these correlations. And this stream, if you actually, let me try to print that out here. It just gives you kind of a memory location. It's a generator object. So this doesn't really print some result out the way you would expect if you had actually done this with a normal function. So the reason for this is that this is actually lazy. So in order to get a value out of it, you would call this next function on something like like stream. And what you have is this first row is the is the initial prices that we started with, and this second row is the next set of prices that this equation is telling you about. I have a feeling there's something a bit wrong here because these numbers don't really follow quite as smoothly from the above, but I think the idea is illustrated. So if I call next once, I get that extra line over here. But if I were to call next again, I get yet another extra line. So it is as though this function, this generator, is kind of remembering for us what used to be its value. So it gives you a value, but it remembers all of these intermediate variables that that we've declared, and it kind of suspends itself until it's called again through this next. So there are a couple of other ways that you could call it as well, but we're not gonna dwell too deep on it. But this is a kind of natural way of representing streams in a language like Python. Um, are there any questions up to this point? I'm going to take that as a no. Yeah, I'm going to take that as a no, unless, yes, apologies. I was just checking the messages. So um, we've kind of illustrated the concept here in terms of our domain. We were looking at financial data, and particularly if this were a stream, you can do this Monte Carlo sampling and kind of generate these numbers. In real life, they're generated at a stock exchange, but this generator idea can actually allow us to hold and deal with paused execution as we saw before. So now I want to talk a little bit about this idea called sketching. So in order to kind of motivate this, I want to think about running statistics. And most of this is actually taken from this library, Rivers documentation, where they have some very nice examples of how you can use this. The idea behind River, which we'll get to in a bit, is that it's pretty much just like scikit-learn. So if you're doing any machine learning in Python, you would be using scikit-learn usually. River follows a very similar interface, but the special thing about it is that it is built for incremental learning. So I'll get to River in more detail in a second, but in particular, what we want to look at is calculating running statistics. So imagine you have a stream of data; it's coming through to you, and you want to keep track of its mean and how many data points you're receiving. So at any given time step t, you have a count nt and you have a mean mu t. And if at the beginning of the stream you might know these values, this might be the very first value, and nt might just be 1. And the way to update these is like this. Nt plus 1 is trivial. You just add 1. That's your next data point. With mu t plus 1, though, it's a little more subtle. You want to take mu t, which is the mean that you had up to now, and then you're going to add x minus x, which is your new data point, minus mu t divided by the number of data points, including the data point that you're dealing with. So if you actually wrote out the definition of mu t and simplify this, you'll actually find that this is equivalent to the normal definition that you're used to. But by writing it in this way, as you'll see in a moment, we're able to implement this as an incremental process of updating this mean. In a similar way, and the maths is a bit more involved here, but it's kind of elegant. You can actually do the same thing for the variance, sigma squared here. This you do through this sum of squares, but in Python, this is actually nice to implement. River actually exposes something called stream, and I'm going to import that as river stream because I imported a stream. I instantiated something called stream above. But what river stream lets you do is after I've got some things out of the way, I again have a number of tickers. I'm going to start a counter at 0, but I'm also going to start some other, I'm going to zeroize some other things. So what I'm going to have are 3 dictionaries: means, sum of squares, and variances. And these are initially just going to be dictionaries with zeros, and they each have a key. They each have the set of keys being the tickers that you're interested in. So what I'm going to do is actually I'm not going to use that stream data set. I'm going to default back to the original data set because of the issue that I had. So I'm going to actually iterate over that data set. So River actually gives you in this stream module, there's something called iter pandas. So either pandas lets you iterate over the rows of your pandas data frame. And this is, perhaps you might think this is a bit better for toy examples like this one. River actually focuses on dictionaries as its preferred way of dealing with things. So this is this is kind of a toy example, but I think it suits us because you can actually illustrate a lot of these concepts. So something to be careful here, especially if you're getting data from an API, is just to make sure that the sorting is correct. You're following the arrow of time. So I'm going to do that. And all I do is just define a standard for loop. Typically, this is designed for X's and Y's. I don't have any Y's in my data set, so I'm just going to go with X here. And for the N, I'm going to implement that equation you saw here. I'm just going to increment it by 1. I'm going to actually store the prior means as the means to begin with. And then I'm going to do my update to the means. So again, I'm going to rely on a dictionary comprehension here. And this is simply this equation turned into, the value of this key value pair in my dictionary comprehension here. So I'm iterating through the items in my original means uh, dictionary. And similarly, I can do same kind of thing for sum of subsquares. It's a little bit ghastly in terms of size, but it's really these equations over here. And what I'm going to do is I'm going to just print those in this same loop. So for each time step, you can see that you've got some means and variances being printed. So at time step 1, here you are. These are the original prices, basically. There's no variance because it's just one number. Next step, you've got 2 numbers getting averaged, and then you've got this standard deviation coming alive. But early on, you can see that these things are a little unstable, and later on, you'll see that standard deviation, for example, gets a little bit, not too much, but a little bit more stable. And this is the kind of programming model for using streaming data with River. And the reason we're doing this and looking at summary statistics is that I want to introduce you to an idea called sketches. So sketches are not really too different from this kind of running statistic that we just saw. You can even think of other summaries. So if you say you try to model your data with linear model and you got your weights out, so those weights are actually some sort of compact representation of how we expect the data to be. So even those weights and that method together, they might consist of a summary of the data. So sketches are really kind of summaries of your data. If you did k-means and you had your centroids, those centroids represent something about the data that you care about. And instead of taking the whole data set with you from one function to another, or some processing job to another, perhaps you can substitute in the sketch. So a sketch is really just a data structure, and it allows you to do some predefined query, some characteristic you're interested in. It could be the mean, it could be the count, or some sort of frequency up to this point, or it could be some other distributional characteristic about your data stream. And you can think of this as a kind of compression because you're not actually having to carry the whole large data set around. You can actually get by with something smaller. There is a kind of formal definition that are in Jelani Nelson's sketching algorithms notes. So a sketch CX of some data set X with respect to some function, and it isn't something so general that you can actually completely substitute the data set. Of course, there's nothing really that nice. So instead, you have some sort of function, and it's a compression of X that allows you to compute or approximately compute F on this X with only the CX. So it's an approximation method. So it's not going to be perfect, but as you'll see, it's actually quite good. some of these methods can rather be quite good. So the method we're going to look at is called tdigest. So this is due to Dunning and Ertl. This method actually allows us to approximate arbitrary quantiles on a data stream. And you can do it in a space efficient way. We're not really going to see that space efficiency because our data set is so small, but we're going to try to actually apply this data set, apply this method rather on our data set. So we're going to use this Python implementation. You just pip install tdigest. And all you do is you import this tdigest class and you instantiate here what I've done is instantiate a dictionary. So for each of my tickers, I have a separate object, a tdigest object. And what I'm going to do is I'm going to use the same kind of loop that River provides iterating through my pandas data frame. And I'm going to update the sketch. So these are my sketches, these tdigest objects. And in each step here, and for each of my tickers, I'm going to just take the relevant sketch for that ticker, the relevant tdigest object, and I'm going to just update it with the new data point. So this is this X that I'm iterating through in my rows. So I've basically come up with, if this sketch is any good, then what I've done is instead of this whole data object, which is a pandas data frame, I now have, for some of the questions that I'm interested, this little dictionary of these objects that ostensibly might be much smaller than your data set, right? It may not necessarily be the case here, but if I were to see how good of an approximation I've got, I'm going to just define this little helper function to print both the quantile and its approximation from tdigest. And I'm going to print the true percentile, and I'm going to also get the tdigest approximation. So here I'm going to use this kind of quantile method on the pandas series. So you've got the median might be something that you're after. So if you look at this, you'll notice that the medians are pretty much spot on. This method is supposed to be an approximation, but it's actually got our medians pretty close. I believe actually pretty much exact. And there's no deviation here. Let's actually be a little harsher. Let's try something like the first quartile. So this is the 25th percentile, of course, and you can see here it's slightly off. You can see in the first decimal place now you can see a slight deviation here, but it's actually quite good because up to up to the ones place there isn't actually too much change that you're seeing. It's actually that good. Let's look at the third quartile. You've got really a similar story going on. But maybe let's check on the edges. Is it really that good on the edges? And it turns out that it's actually here you're now seeing the ones place getting changed. So at the edges, the algorithm might not be quite as strong here. You can see some of these deviations starting to pop up on those edges. But if you really care about where most of the mass of your data set is, then tdigest might be a very good way to approximate quantiles that you care about. So the nice thing about it is that this tdigest object doesn't have just the quantile that you care about, because we only we had to update the tdigest objects in one loop, but I can now query it for any of the percentiles that I care about here. So in this way, it's really quite nice, and you can actually look at the implementation through this nice two-dict method here. So it's relying on these centroids. So there's some sort of clustering going on. I won't go into details, but the way this works is that you have through the empirical CDF that you saw before, the procedure to generate your t-digest starts creating clusters all along that, and it tries to gather more mass along the kind of binning that it does, and the in this way it's able to kind of store a more efficient representation. But I really recommend the original paper and even the blog that's around the Python package for more information here. Um, there's another nice feature to this. If you take kind of the median of a data stream, let's actually forget about streams and just look at a data set. You've got it as a list of numbers. If you take the median of this thing and you have another couple of lists, you take their medians as well. Now, suppose that you have this set of medians, you put them in a separate list, maybe call it medians. Um, but you've also got the original numbers, right? Suppose you took the original numbers, you concatenated them, you ordered them, and you took the median of that. Versus if you took the median of the medians that you collected, they're not usually going to be equal. So with quantiles, you have this kind of problem where it's very hard to compose them. But with T-Digest, I claim, and you can find out for yourself, that these can actually be combined in a sensible way. So this can be really useful, especially if you're working in a distributed setting, as you might well be when you're dealing with very large data streams, because you can actually compute your T-Digest at perhaps at different times. You've got sequentially um, one bit of the data stream being processed by one node, and it's generating a t-digest. The other bit is another node, and it kind of goes in this round robin fashion. And when you kind of have all of these kind of mapped out, you want to reduce this to the statistic you care about. Maybe you care about getting the median of this. So what you can do is you can add up all of those different t-digest objects that you get out of all of the different nodes. You can collect them, you add them up, and there's this kind of combination operation that relies on the same kind of idea that I was telling you about in terms of the clustering. You add them up, and then if you take the percentile out of that object, which is again itself a t-digest, what you'll find is that it is actually representative of the real median. So it's approximating the real median of the full data set. Um, and that's really a nice property for this kind of application. So you could use this if you were interested with something like Spark streaming. You can certainly use T-Digest. I'm going to skip over illustrating T-Digest, and I think in favor of time, I'm going to actually skip over some of these pieces as well that I haven't really sketched over as well as I'd like to. And I'll go directly to elaborating on more things you can do with the River package that I illustrated. So we've only really used River for its iteration capabilities, that kind of stream submodule that I imported, but it actually has quite a bit more. So first, I'm going to illustrate something that is quite similar to a batch learning setting, but I'm going to use the River API, and I'm going to actually try to learn uh, uh, create a model to learn something interesting one data point at a time. So the data set that we're going to use, I'm not going to use the financial data set here because this is a little bit easier to illustrate. The data set we're going to use is about breast cancer. So it's this breast cancer data set that is found in scikit-learn that I'm going to use. And this data set has a bunch of attributes. It's actually trying to, the purpose of it is, given those attributes, can you actually predict whether a woman will have breast cancer or not? So that Boolean is your Y variable, and you've got your independent variables, and those are those attributes that are in the data. So I'm gonna import some familiar things, but also new things, because if you're familiar with scikit-learn at all, you have this kind of submodules in there. So from sklearn also you can import pre-processing, ensemble tree, compose, metrics, and so forth. But instead, I'm actually going to import those from River. I've set a seed just to be reproducible in what I'm going to do. And I'm just going to define a scaling. So the way this scaling works is actually harkening back to how we did our running mean and our running variance. So the standard scaler that comes with scikit-learn actually uses those. It tries to scale your data so that it has zero mean and unit variance, as it says here. So what this standard scaler from River is going to do is at each time step, it is going to make sure that the same holds for now your streaming data set. So it's very similar, exact same kind of instantiation. I'm going to use a particular model that I wanted to actually elaborate on to do with something else, but I didn't get a chance to. But this is something called the AdaBoost classifier. So a boosting model is something that takes a bunch of weak learners and it progressively tries to model the error of those weak learners so that you get better models through ensembling them. So what we're going to do is we're going to take this special classifier called a Hofting tree classifier. I might be mispronouncing that name, but these will be our base classifiers. They're not very good. They're like decision trees, basically. And the AdaBoost is like, if you haven't used AdaBoost, it's like a gradient boosting machine. And it has an interesting implementation that I won't go into detail here. But what I'm going to do is I'm going to define this model and I'm going to actually make it an ensemble model, this AdaBoost classifier. So AdaBoost actually takes in another model. So you would then feed in this Hofting tree classifier in there. And I'm going to go with like 5 of those models, and I'm going to, have my seed there to make this reproducible. And then I'm going to define a pipeline, just like I would in scikit-learn. River also has this kind of compose submodule. And from compose, I get this pipeline class. And into pipeline, I give, I can name my steps. I can bring scaler in here as here I'm scaling things. Here I'm modeling things. It's not very different here, so you might not really see the value, but this can actually help you create a reproducible and nicely separated out pipeline. So once I do this, I'm going to actually follow the exact same tutorial that's available for River, and in a very similar way, I've just changed the models really. So you've got your ground truth in y true and your prediction in ypred, and these are initially going to be just empty lists. What I'm going to do is also I'm going to actually define my metric. I'm going to instantiate my metric. I'm going to look at the area under the curve of the receiver operating characteristic curve. So I have to actually instantiate this here, and you'll see why, because I'm again going to use this river stream, and I'm going to iterate. Now, instead of a pandas data frame, I'm going to iterate through this breast cancer data set. I'm going to actually shuffle it, and I'm again feeding the seed number in here. And now I've got X's and Y's. The X's, as I mentioned, are going to be your features, and the Y is whether the woman had breast cancer or not. So what I'm going to do is go one by one, because this loop is going to give me row by row of this data set. So after it's been shuffled here, and I'm going to make a prediction. So there's a new sample, a new Xi. I'm going to predict the probability for one, and I'm going to do that for Xi. I'm going to then train the model using this learn one method. I can do that through the whole pipeline just like this, and it behaves just like a model. So I'm going to feed it not only the X's that I used here, but the actual Y value. So now my model has been updated. I'm going to store the ground truth here by appending to this list, as well as appending to the predictions over here. Um, and because I use this predict proba, I'm gonna have to use this over here. But I'm also going to, in the same step, update the metric. So this metric object that I instantiated here has an update method. So I'm gonna call that with the ground truth as well as the predictions, and I'm gonna keep printing that metric. And at the end, I'm gonna just try to print the final metric as well. So as you can see here, I've kind of given the game away, but as you can see here, each step, initially it's not learning much. Then it sees like, 5 data points. It's somewhat okay, and then it keeps progressively getting better. It sometimes gets worse, and then it gets better again. The more it's seeing, it's able to learn one at a time, one data point at a time. So at some point you get to, 80%, and then you actually go into 90%. With scikit-learn, with a similar setup, you might be able to go very high. You might be able to go like 90, 97, 99%. But here we're getting to something like, um, yeah, we're getting to like 96.68, which is actually quite, decent, although this might be a bit of an easy data set. So I've tried to illustrate what River can be helpful with in terms of stream processing, but also in general, how you might want to represent a stream as well as learn on a stream. One consideration might be that we're using some of these models like the Hofding tree classifier, and those can be presumably quite sensitive to the data distribution. So if the data distribution actually shifts along your data stream, so suppose you're a internet company and you have a social media app, you have a kind of clickstream data set. Let's say the frequency of somebody of your users, going to a particular feature and clicking something and buying something, perhaps. But now, if you deploy a change in your web app, now you may have affected that, right? You may have made the buying easier or more difficult. So now you have a different distribution of users by behavior. So this kind of drift, sometimes so if you actually purposely intervene that way, you might know that something different happened. But sometimes there are factors beyond our control and maybe beyond our notice that you might want to be sensitive to. So one way of actually keeping an eye on those things at low computational cost as well as low memory is to actually use something like tdigest, a sketch. So these sketches can tell us when the data is uh, a little bit off from what we're expecting. And there are certain approaches like this paper that I've linked here that looks at, looking at the distribution, looking at perhaps applying a parametric or a non-parametric test to make sure that your distribution is actually following. And you don't have to compute your distribution on the whole massive data set in order to do this, because you've got something like tdigest. You can do it on these very good approximations. So that's pretty much what I have for you today. I could not, unfortunately, cover something that I intended to, which is the multiplicative weights update method, as well as how is tdigest actually working under the hood. But there's actually more to stream processing than just what I went through. There is reinforcement learning. So the setting in reinforcement learning is actually very conducive to looking at it from a stream perspective, because you've got an agent, the agent is out in the environment, and every step they make an observation, they have some internal policy, and according to that, they're going to take an action. And once that action is taken, the observation changes, but they also get themselves some sort of reward from the environment. So, and that reward function might be defined in various ways, might sometimes be absent, but this setting, because it proceeds very sequentially, is an actual one for streaming. Similarly, you've got other types of sequence modeling problems We looked at some here in the machine learning case with stock prices. We looked at the kind of breast cancer data, but that wasn't really time sensitive. But you may have situations where that is the case if there's an intervention being delivered and you have a massive study going on. But even for things like audio and video feeds, these can be sequence modeling tasks. And even reinforcement learning these days is sometimes approached in this way. And again, sequence modeling really fits this streaming paradigm. And can you learn either in one at a time, or can you learn in little mini batches in such a way that you're sensitive to the hardware constraints that you might have? I did not really talk about async I/O. The reason I bring up async I/O is that it's the kind of the standard way now to do concurrent programming and doing coroutines. I showed you something of a coroutine with the yield keyword back when I was trying to simulate the stock price paths. But async I/O is something you'd probably want to have a look at if you were actually looking at streaming data. And then there are, of course, these big data systems. They're not necessarily written in Python, but there are Python APIs, and they leverage various techniques in order to distribute jobs that may not fit in one computer core. And you can actually do this with data streams as well. I gave one example of perhaps using tdigest in a kind of map reduce setting where you've got your at different intervals being digested at different nodes and then reduced together because of that monoidal property that you had in tdigest. But these are a little beyond the scope of this. And I've got a few references here. I've actually peppered some references throughout this notebook in terms of what I've used as the basis, as well as further reading. And I will make this notebook available to you. So that's pretty much what I have today. Thank you very much for listening. Any questions?
Yeah, so there are two questions in Q&A session. Let me show those things in.
All right.
Yeah.
Okay. So first one, I think Yahani asks, can you explain what is the output of the generator from the Monte Carlo? How do you interpret that? So I think if I go back up here, so it's around here. So I've created this generator. I believe there is a bit of a mistake perhaps in how I'm using the Cholesky decomposition or something in the formula, but ideally these prices should not vary this much. So if this was the initial set of prices, and it is, this can't just go to zero like this. So I've noticed like a bit of a bug in this code. I'll have a look at that. But in terms of how it works, what you're doing is let's forget all about all of the different complicated things happening here and the complication of this formula. What's really here is you've got a function and you've got a loop in that function, and you've got some things instantiated, maybe inside the loop or outside the loop. And then you've got this yield going on. I'll actually skip this other for loop as well because it's not pertinent. So what's happening here is that when you define the function this way, and it's a generator because we use yield, what you can do is you can progressively ask for values from this function. So even though the function is actually defined for this whole range of this loop, you don't have to get it all at once. You can get one by one the prices. So this is what I'm actually doing here by I'm instantiating my function by giving it the arguments that it expects, and then there's this thing called stream. But if I try to print stream, it's actually lazy. It hasn't actually done much. It's just got a memory location for the way I defined it. But by calling next on this stream, that's how it generates, the next value. And it still doesn't care about the other values as you see here, even though, I run up to t plus 1 and t is like 120. So it should, care about all of those, but it doesn't. I've just instantiated these to 0, but you can actually imagine a scenario where I haven't taken up any memory at all, right? And I'm asking for this not in a numpy array, but I'm asking for like, you know, um, a set at a time. So what I don't have to do is I don't have to like, call the function multiple times. Instead, I have the same function and I'm able to call this next method and I'm able to kind of exhaust it uh, iteratively. And the reason I can do that is because this function actually, this yield actually is giving me out of this function, the return is actually an iterator. And that's why I can like iterate like this. So it looks a little funny because I've actually taken up the memory with these zeros. But if I didn't, um, you'd have something lazy that is only giving me what I want when I ask for it through this next. So I hope that kind of clears it up. Um, so I have another.
Yep.
Okay. I've got a. Yeah. So the tickers were correlated, right? So the tickers are actually just the labels. So the price series for those tickers were correlated. These here. So in order to deal with this correlation is why I'm actually using this whole Cholesky piece over here. It hasn't really, taken the way I expected, I believe, and that's why I'm getting funny values over here. But um, but theoretically, the correlation should be handled in this way. I won't really go into the nitty gritty of why that is, but this is something that you can look up in a standard kind of financial text, or perhaps even Wikipedia.
Um, I think that's all the questions, guys. If you have any other questions, you can raise them here in the chat or Q&A session, or you can just raise your hand. We can get you into the stage and we can talk. So, and one more thing, Yasuro, can you share the collab sheet with us so we can share this thing in our YouTube descriptions?
Yes, absolutely, I will. I just want to fix that little bug, and I will share that with you.
Yeah, yeah, sure, no problem. So, I think that's all the questions we have. Yeah, then shall we conclude? So, Yasiru, so thank you very much for having time to organize this practical session actually. So it's not just a presentation, and me myself have worked with scikit-learn, but I haven't worked with the river package, and I have worked with this kind of normal data, not with streams. So it's very good to know these things, and I was always wondering how these guys handling this kind of continuous data streams. So thank you very much for your knowledge and knowledge sharing with us. So again, thank you very much for your time, and you having time to prepare all of those things for us. So I think we'll be able to meet you soon again with next sessions. So if you have time.
I
So
hope so. I hope so. Thank you very much for having me.
yeah. So then bye bye for until the next session.
All right. Thank you, everyone.
Yeah. Thank you, Yasir. Bye.